Good morning, my name is Jose Miguel and I will talk about how to apply HODMD analysis in a force flow over a backward forcing step by harmonic perturbation. This technique falls in the framework of subcomputing methods. This work has been done in collaboration with Soledad Leclerc and Jose Manuel Beca. This presentation consists on the following items. I will start with the motivation and aims. Classical non-model analysis has a technical limitation imposed by the adjoint problem, which is solved assuming homogeneous derived boundary conditions in all the boundaries. In this work, we will try to avoid this problem solving the non-modal stability analysis using the data-driven method high-order dynamic mode decomposition. Therefore, the choice of boundary condition will not be determined by any restriction. The objective of this work is to develop a procedure that allows the characterization of transient growth perturbation using HODMD analysis. For this end, this work studied in detail the energy amplification produced by inflow excitation of a steady flow over a backward forcing step. During this presentation, the procedure is particularized to fluid dynamics, but this could be generalized to another fields. High-order dynamic mode decomposition is a method introduced to analyze flow fields and identify the spatial-temporal patterns. This algorithm is a generalization of dynamic mode decomposition proposed by Smith in 2010. This algorithm has been applied successfully for extracting spatial-temporal coherent structures from data. These structures, often called modes, have a given frequency, a growth rate. This method decomposes a given spatial-temporal flow field as a series of expansions of Fourier-like modes in time and space in some spatial coordinates. Given a continuous time dynamic system like this, the generalized Gutmann assumption states that the solution can be written as follows, where VA are j-dimensional snapshots equidistant in time with time interval delta t are the linear operators, and the aim is to calculate the DND Gutmann expansion given by the following expressions, where Bn are the modes, An the corresponding amplitudes, and alpha n and omega n their temporal growth rate and frequency respectively. HODMD algorithm considers the following snapshot matrix. The method considers only two steps. First, a singular value decomposition is applied to the snapshot matrix and therefore the DND modes are computed. When d is equal to 1, we have the classical DND algorithm, and when d is bigger than 1, we have the high-order DND algorithm. This slide describes the problem of the study. The computational domain is represented schematically in the following figure. We have a two-dimensional channel with solid walls up and down, inflow at the left and outflow at the right. Inlet and outlet heights are h and 2h respectively, being the height step equal to 2. The length of the inlet and outlet is 10h and 50h respectively. The Reynolds number is defined by using the velocity at the center channel, h, and the kinetic viscosity. For Reynolds number equal to 500, the flow is moderately stable but unstable by transient growth. The base flow was calculated using sentence, which is a numerical solver that solves the incompressible Navier-Stokes equation using high-order finite element methods. The method is defined by using 563 rectangular macro elements with 7 nodes along each edge. These nodes are placed at the set of Legendre polynomials defined in the canonical square that this may be to each macro element. Non-slip boundary conditions are considered at the solid walls up and down, a parabolic Poisson profile with a central line velocity equal to gc at the inlet and zero traction outflow boundary condition for velocity and pressure at the outlet. Given the steady base flow, the linearized Navier-Stokes equations are integrated assuming zero initial condition and the following boundary conditions at the inflow, where tau is the final time, sigma is a positive relaxation parameter with allows a small transition at the beginning and the end of the simulation, and omega is an angular temporal frequency. The term UV is modeled so that each component is expressed as a convergent series of sine functions with p equal to 2. In contrast to what is generally done in a classical nonlinear analysis, the outflow boundary conditions applied in the linear solver are the same as the one applied in the calculation of the base flow. Newman boundary conditions for velocity and the remaining boundary conditions are homogeneously let for all variables and boundaries. When the numerical simulation is converted, we collect a group of snapshots to apply HODMD and create the DND expansion. Bk is the result of the numerical simulation at time tk. In this equation, URN and UAN are the real and imaginary parts of the amplitude UM. Note that in this equation, the first term is for complex conjugated modes and the second one is for real modes, so UN is real for n bigger than n. This slide defines the process of predicting the optimal perturbation for a given value of the angular temporal frequency omega at the inflow. This methodology is more general, allowing to introduce a range of angular frequencies at the inflow. The maximum energy growth G at time tau is the maximum ratio between the final energy in the world domain and the energy at the inflow for a given frequency. This is the inner product defined as the integral defined in the world domain. This equation solves the generic perturbation at time t, where MP is the temporal evolution of matrix M0 and B is a column vector which defines the amplitude of optimal modes for a given inflow perturbation. Then we apply the singular value decomposition to matrix M0 and MT, where B and W are the left and right singular vector and sigma is a diagonal matrix containing the singular values. Then solve this optimization problem over all possible combinations of inflow boundary perturbation is equivalent to find the large eigenvalue of the following generalized eigenvalue problem, where f hat and b hat are defined in the following way. Once the amplitudes of the optimal mode have been calculated for a given time horizon tau, it is straightforward to obtain the state of the optimal mode in the following way. We will show some results on the following slides. The HODMD analysis has been performed considering the following parameters for epsilon 1, this is the tolerance in the singular value decomposition, and epsilon 2 for DND analysis, and we consider d equal to 1. The initial perturbation tries to estimate the relevant modes necessary for the optimization process. These perturbations are evolved in time using a linear solver of the Navier-Stokes equations. The following figure shows the solution obtained for the gain. From left to right, omega goes from 0.5 to 1 to 5. As we can see, G decreases when omega increases. Mao observed similar behavior in the evolution of the energy, although there are some differences found in the value of the energy growth. One of the main reasons for these discrepancies could be related with the different boundary perturbations used in our case. The following figure shows the span-wise vorticity for different values of omega. From top to bottom, omega goes from 0 to 5 to 1 to 5. These structures are similar to those obtained in Mao, observing the same pattern in the case of omega equal to 0.5 and recovering part of the activity of the mode in the region near the step in the case of omega equal to 1 to 5. As conclusions, a novel optimization methodology for the analysis and prediction of optimal perturbation has been introduced. The disturbance tries to excitate the relevant modes necessary for the optimization process and are evolved in time using a linear solver of the Navier-Stokes equations. These modes are calculated applying the data-driven method HODMD to the database generated in the linear integration. Once the domain modes are characterized, an eigenvalue problem is solved, being its leading eigenvalue the maximum growth rate and its corresponding eigenvector the coefficient to use in the reconstruction of the optimal perturbation. The results obtained are promising, showing the expected trends in both the growth rates and the set of modes. The difference found in the maximum energy level encourage the authors to continue improving the method presented in this work.